In this video, we'll continue to look at electricity. We will be looking at series and parallel circuits. We'll talk about what exactly it means to connect components in series as opposed to what it means to connect components in parallel. And we'll also mention the main characteristics of components connected in series as well as components connected in parallel. All right? So let's look at series circuit first. Now, when we hear the word series, when most people hear the word series, automatically they think of TV shows. TV shows where basically the episodes come one after the other, right? So we call it a series. Now, in a circuit, the thinking is not that different. When we say that components are connected in series, it basically means that they basically come in line one after the other, right? So we have circuits here where we have a circuit on the board here where we have three lamps, L1, L2, L3. They are connected end to end, and therefore we say that in this manner they are connected in series. If we were to look at two wires, for instance, if we were to take these two wires, and we'll basically connect them like this, with the other ends going on to connect to opposite. So let me just add a third one. We're to connect a third one like this. Then of course we could say that these wires of course are connected in series, right? So we connect them end to end, and essentially the wires are connected in series, right? So basically this is what is happening here. So in this case we have three lamps, L1, L2, L3 are all connected end to end, and we say that they're connected in series, right? Now let's examine the circuit in greater detail. Now in the circuit we have a battery. So we know the circuit symbol for a battery. A battery is a group of cells. A single combination of long and short stroke is a cell. A group of them is called a battery. So here we have a battery, and we've indicated the positive terminal or the higher potential of the battery and the negative terminal as well. Now, as previously indicated, of course, whenever we have a battery in a circuit, then of course we are expected to show the direction of the current flowing around the circuit. And we've also explained the concept of conventional current, and it basically said that conventional current would flow from the positive terminal of the battery and would therefore flow in the opposite direction that electrons, which are negative charges, would actually flow. So therefore the conventional current I is flowing from this positive end of the battery and goes around this circuit in a, anti-clockwise direction. Now in this circuit, of course, we also have an ammeter labeled A in the circuit, and we have lamps L1, L2, L3 connected in series. We've also identified 3 points along the circuit, say B, C, D. Now, we'd have done an experiment in school where we basically looked at series and parallel circuits, and we're able to determine some of the characteristics of those circuits, and of course we'll be talking about them in theory here. So what we have before, as I said before, is that we have three lamps, L1, L2, L3 connected in series. Now let's talk about the current first in the series circuit, right? So let's talk about the current. Now, this is an ammeter, and of course the purpose of an ammeter in an electric circuit is to measure the current flowing. So basically, if we were to take this ammeter from this point and place it at B and measure the reading, then remove it from B and place it at C, record the reading, remove it from C and place it at D and record the reading, what we would have observed in each case is that we get the same reading, right? So if you were to remove the ammeter from where it's currently connected, place it at B, take the reading, then place it at C, take the reading, then place it at D and take the reading, then what you would have observed and what we did observe in the experiment was that the reading is the same. And what this basically goes on to tell us is that in a series circuit, the same current flows through all points in the circuit, right? So in other words then, when components are connected in series, the same current flows through each of those components. So we can make a statement here by saying that we can say that the same current flows through all points in a series circuit, or in a series circuit, right? In a series circuit, the current flowing through each point is the same. Right? So that is basically the first property of series circuits that we'll actually mention. So generally, if components are connected in series, it means that basically the same current will be flowing through them. And it doesn't matter in which direction or where, at what point in the circuit to actually place the ammeter will always give the same reading, right? So mention now, we spoke about the current. Now let's talk about the potential difference across these devices. Now let's say we have a battery with supplying a voltage V. Now we clearly see that we have lamp L1, and the PD, or the potential difference across lamp L1, is given as V1. We have lamp L2, and the potential difference, or the PD, across lamp L2 is V2. Also, we have lamp L3, and the potential difference across lamp L3 is V3. Now, what we would notice is that basically, if we should take a voltmeter and connect it across lamp L1, then connect it across, or let's say we have 3 different voltmeters, right? Let's say we have 3 different voltmeters of very high resistance, and we connect each of them across L1, L2, L3 respectively, and of course we have a 4th voltmeter that we will connect across the battery. What we will observe, or what we ought to observe, is that the reading on the voltmeter connected across the battery, let's call that V, will be equal to the sum of the readings of the voltmeters are connected across L1, L2, L3. So in other words, then V is equal to V1 plus V2 plus V3, right? And so this basically we would be able to observe if we were to basically build a circuit and actually take these measurements. Now in practice, these values might not be identical, but they ought to at least be very, very close. You know, they could be not identical due to additional resistances in the circuit and so on. But of course, in theory, they're supposed to be exactly the same. In practice, they'll be very close, but not necessarily identical. But close enough for us to say that this relationship is true, right? So basically what we're saying is that whenever we connect components in series, the total PD across them is equal to the sum of the individual PDs across each, right? So when components are connected in series, the total PD across them is equal to the sum of the individual PDs across each. So let me write that down. The total PD across components in series equals the sum of the individual PDs across each. Right? So basically what we've done so far is essentially summarize the properties of series circuits. Right? In the first case, to say that the current flowing through each point in the series circuit is the same. So once again, if you have 3 lamps connected, L1, L2, L3 in series like this, we measure the current flowing through, then we get the same whether we place the ammeter here, or at B, or at C, or at D. If we were to actually take 4 voltmeters, connect 1 voltmeter across lamp L1, another across lamp L2, another across lamp L3, and the 4th voltmeter across the battery, then when we actually compare those readings, what we would observe, or we ought to observe, is that the reading across the battery, or the voltmeter across the battery V, is supposed to be equal to the reading across L1 plus L2 plus L3. So therefore V is equal to V1 plus V2 plus V3. And from that we can actually conclude that the total PD across components in series equals the sum of the individual PDs across each. So what exactly does this mean? Let's say, for instance, the PD across this is 1 volt, and this would say 2 volts, and this is 3 volts. Then 1 plus 2 plus 3, that will give us 6 volts. And if those 3 then add to give 6, then the PD across this battery ought to be 6 volts. Good? All right, so let's now examine our parallel circuit. Now, clearly, we can see that these 2 circuits are not the same because the manner in which the lamps are connected is different, right? Now, in the series circuit, when the current is flowing, essentially the current has only one path through which to flow. And basically, as the current flows through each of these lamps, there's going to be a voltage drop across each lamp. And of course, we can measure that voltage drop using a voltmeter, right? Good. Now, looking at the parallel circuit, we still have our battery. Let's say we have a battery supplying a voltage V. Now, once again, the battery is driving a current. And of course, remember that when looking at circuit diagrams, what we indicate as our direction of the current is what we consider to be conventional current, which of course is the direction that positive charge would flow, right? So despite us knowing that electrons are really the mobile charge carriers, we do not indicate the direction of electron flow in a circuit unless we're required to do so. We typically indicate the direction of conventional current, which would basically be the direction that positive charge would move, right? So we have the conventional current I flowing around the circuit. Now let's see what happens when this current flows. Now when this current flows, basically what it encounters here is what we call a junction. Now this little symbol right here with this dot is a junction. So if we have a wire, something looking like this, then that basically right there is a junction. And a junction in an electric circuit is where two wires are connected. So similar to a junction in a road where basically two roads connect or meet, then a junction electric circuit is where two wires are connected. And of course, you should be able to differentiate between where the wires are connected as opposed to where they just cross, right? So this is meant to indicate a junction where the two wires are connected. However, if it looks like this, then it basically means that the two wires, they just cross. They are not connected to each other. And we can actually demonstrate this using two wires, right? So let's say if these are our two wires, then obviously for them to be connected, then these are two wires being connected like this, and this would basically represent a junction. However, if this wire simply crosses over this one like this and goes on to be connected somewhere else, then this of course would represent the wires crossing, which is indicated by this, right? So we need to be able to differentiate between a junction where two wires are connected and where the wires simply just cross over each other. Right, so let's proceed. So what we basically have is that let's just label our junctions. Let's call this junction A, junction B, junction, well, this won't be a junction, but let's call this let's just call this point C, but this is junction A, junction B. Anyways, right, let's just junction here. Yeah. So let's analyze what is happening, right? So basically this battery is driving a current around the circuit. The current basically reaches at junction A. Now the current basically sees multiple paths in which it can actually flow. So what does the current do? Does it decide, hey, I'm going to only flow in one direction, I'm not going to flow in any of the other parts? No. Instead of doing that, what the current does is the current splits. The current splits. A portion of the current flows through one path, in this case towards lamp L1. Another portion of the current, or the rest of the current, goes on to split further at junction B. So another portion of the remaining current will then flow towards L2, and the rest of the current will then flow through lamp L3. Now we looked at, we spoke about resistance in briefly. We haven't examined resistance in great detail, but when we speak about electrical resistance, we're speaking about the opposition to the flow of charge or to the electric current flowing, right? And what happens is that the greater the resistance, then the smaller the current that will actually flow to a particular part of the circuit. So what this means is that if we have a circuit with multiple parts and there's a greater resistance in one path, then it means that the smaller current will actually flow to that path. The path of least resistance, that path will actually attract the largest current. And generally, current tends to flow towards the path of least resistance. In other words, then, the smaller the resistance in a particular path of a circuit, then the greater the current that will actually be flowing towards or in that part of the circuit. So basically, as I said before, without taking the magnitude of any resistance of these parts into consideration, we basically know that there are three possible paths for the current to flow, and therefore the current does, it will actually split, and lamp L1 will get a portion of the current, let's call that I1. Lamp L2 will get a portion of the current, call that I2. And lamp L3 will also get a portion of the current, we'll call that I3. Now, if we were to take, where's my eraser? If we were to take, for instance, 3 ammeters, if we were to take an ammeter and connect it here, right? Make some space. If we were to take an ammeter and connect it, say, here to measure the total current, let's call that A, right? If we were to place an ammeter there, that would basically measure the total current I flowing in the circuit. If we were to take 3 more ammeters, place one here to measure current I1, one here to measure current I2, and the other here to measure current I3. Or as I said, as we mentioned before in the previous series circuit, it doesn't matter the point, so we could actually place it here. Let's just put an ammeter here. Let's call this A1. Let's just put an ammeter here. A2, and let's put an ammeter here and call this A3, right? So yes, if we're to place 4 meters in the circuit like this, where this ammeter essentially be measuring the total current A, and this A1 will measure the current I1 flowing through lamp L1, A2 will measure the current I2 flowing through lamp L2, and A3 would measure the current I3 flowing through lamp L3. So if we were to basically modify the circuit like this and observe the readings on these ammeters, then what we should be able to observe is this. The reading on this ammeter labeled A should be equal to the sum of the readings on ammeters A1, A2, and A3. Right? So once again, if we were to modify the circuit and include these ammeters, the reading on this ammeter should actually be equal to the sum of the readings on these 3 ammeters. And from this, we can basically conclude that in a parallel circuit, the total current flowing is equal to the sum of the individual branch currents. So we can basically sum this up in an equation to say that I, the total current, is equal to I1 plus I2 plus I3. Right? So we can say that in words to mean that the total current is equal to the sum of the individual branch currents, right? So we can say the total current flowing equals the sum of the individual branch currents, right? So this is basically one first property of parallel circuits. So when components are connected in parallel, the total current flowing equals the sum of the individual branch currents. Now, similar to what we did when we looked at series circuits, we'll also examine what is happening to the voltage or the PD across these components. Now, if you notice that basically we say the battery is V. Now, these lamps are connected in parallel as indicated. If we were to take a high resistance voltmeter and connect it across the lamps, then it will give the same reading as if we were to connect a voltmeter across the battery, right? So connecting a voltmeter across, as a matter of fact, connecting a voltmeter across any of these components, whether it's the lamps or the battery, will give the same reading. And so this leads us to conclude that when components are connected in parallel, the PD across them is the same. So for components connected in parallel, the total current flowing is equal to the sum of the individual branch currents, and of course the PD across each component is the same, right? So we can write that the PD across each component same. And here basically we have summarized the characteristics of series and parallel circuits. So once again, for parallel circuit, whenever we have a set of components connected in parallel, the total current flowing is equal to the sum of the individual branch currents, and the PD across each device or each component is the same. And this applies whether it is a lamp, a resistor, or some other electrical device which basically uses up electrical energy, right? So once again, if we were to take a voltmeter connected across L1, L2, then L3, would get the same reading. And because each of these components or devices are connected across the battery, that reading would essentially be equal to the battery voltage. So this summarizes our look at series and parallel circuits. And of course, we were able to examine the characteristics of both circuits. In the case of series circuit, we said that when components are connected in series, the current flowing at any point in the circuit is the same. And of course, the total PD across the components is equal to the sum of the individual PDs across each. When components are connected in parallel, however, the PD across them is the same, and the total current flowing is the sum of the individual branch currents.